All right, so we should have our bell ringer done. Let's dive into what we're going to start today. And like I said earlier, we're doing earth science now. We're moving past that life stuff. We're digging into some really fun earth science. So, what are we going to do today? Today it says that I can use index fossil records to create a timeline of Earth's history. That sounds kind of complicated, but it really isn't that tough. And I think we've heard of fossils before, maybe not index fossils, but we're going to learn it today. So, like I said, we've probably heard of fossils in one way or another. What are they? Fossils are just the remains or evidence of ancient or super old living things. So, this is just a piece of evidence that shows that millions of years ago, this thing was living on the earth. So, it's typically going to be bones, like in this big skeleton here, and this is actually in a museum in Jackson, Mississippi. So, we have a lot of fossils you can see even in this state. So it's usually going to be like the bones or a skeleton. It can be like here's a dragonfly that turned into a fossil, and it doesn't have to just be an animal. Here's a plant. Here's another skeleton over here, and this right here actually isn't a body part. This is actually dinosaur poop. So if you thought that thing looks like poop, you are correct because it is poop. So fossils can be a number of things. It doesn't have to actually just be the living thing itself. It's just any evidence that something there was living millions of years ago. So we have a giant collection of all the fossils we've ever found, and we call this the fossil record, just the record of fossils. That's pretty easy. And we use our fossil record to learn more about the history of Earth. So if we see that certain living things were around during a certain time period, we kind of can draw this beautiful picture of what did life look like here millions of years ago. Because right now we're here and we've got deer, we've got squirrels, we've got certain types of trees, but perhaps millions and millions of years ago, we didn't have squirrels, we didn't have us, we didn't have what we have today. So we can look at these fossils to figure out, okay, what did the earth look like at this time period? And I'm actually going to show this very short video that explains like what even is a fossil, how is it made, like how does this happen? So let's watch just like the first minute of this.
Millions of years ago, this dinosaur was going about his normal daily life. But his day went from good to bad, really bad. After he died, other dinosaurs ate him, and the rest of his skin and muscles rotted away, leaving just his bones. These were quickly buried by mud. Over millions of years, more layers landed on top: mud, sand, and even volcanic ash. This added up to a lot of weight on top of the skeleton. Some parts got crushed. The layers of mud, sand, and ash turned into hard, sedimentary rocks. While this was happening, water seeped into the bones. It left behind minerals, turning the bones to stone and creating a fossil. Earth changed a lot over millions of years. Rocks that were once deep underground rose to the surface, a process called uplift. Very slowly, wind, water, and ice wore away the rock. Eventually, bits of the fossil skeleton were exposed and became visible on the surface. Fossils are constantly getting eroded out of rock. Most are lost. But if we're lucky, someone will find one.
Okay, so that is exactly how fossils are going to be formed. You have your living thing living on the surface of the earth, then it dies, and then it becomes buried and turned into a hard structure, and then on top of where it's buried, another living thing lives, and then it dies, and then it's buried, and it's just a process that never ends. So, when you think about that, thinking about how those fossils are being formed, if we took a slice of the earth right now. So like looking at this picture right here. Up here is the ground where we are walking on today. And this is what you're looking at. You can think of like a piece of cake. You know how when you cut into a piece of cake and you pull it out, you can see like the inside or the layers of the cake? That's exactly what we're looking at here. So this is, if you dig deep into the earth, this is further down into the earth. So since we are talking about the fossils, living on the surface, and then they get buried, and then on top of that is another living thing, and then they get buried. We know that the further down you go, the longer amount of time ago that living thing was present. So like today, here we are at the top. So if you think like, let's just say 1,000,000 years ago, at one point this was the surface, and all of this was below it. So then when this was the surface, it was much longer ago. So the further down you get, the older the rocks and the fossils in that layer are going to be. So the youngest rocks and fossils will be at the top, which means the oldest are going to be at the bottom. That's pretty easy. So we have a term for this, a term for the fact that the youngest is at the top, the oldest is at the bottom. We just call this the law of superposition. So you can just think about the position of those rocks and fossils. So the youngest at the top, oldest at the bottom. So like I said, the fossils are going to be the same. That's all this picture here is saying. So if we have fossil A is going to be much younger than fossil B, which is younger than fossil C, which is younger than fossil D. I think that part's pretty easy, so let's go ahead and move on, shall we? Okay, so we as scientists have two different ways that we are going to determine the age of a fossil or a rock, because just finding a fossil isn't giving us too much information. It's super helpful to know how old this fossil or rock was, so we know, okay, this living thing was around during this time period or this many years ago. So one way, and I'm actually going to go to the right first, we can use absolute dating. And when we say dating, that just means that you are assigning a date or an age to that thing. So when you use absolute dating, you are finding the actual age, or like whatever you're going to represent it by a number. So like your absolute age would be 14 or 13 or however many years old you are. So there are different techniques that scientists use to absolute date a living or a fossil or a rock. It usually has to do with very intense processes that you have to go through a lot of school to do. So we can't really absolute date any fossils ourselves, but if you become a scientist, you absolutely can. So a good example is if you say rock A is 120 million years old. That would be an absolute date. Or if you say this thing was alive 140 million years before present, or 140 million years ago. That is absolute dating. What we can do, even though we have not become doctors and haven't gotten a job where we are absolute dating these fossils, we can do what is called relative dating. So when we talk about relative dating, we're not giving an exact age, so we're not really going to use a number for it. We're just comparing the age of one fossil or one rock to another. So you can say that rock A is much older than rock B. That's like saying if you have a younger sister, you would say that your sister is younger than you. So you're not giving an exact age, you just know one is older or younger than the other. So if you look at this picture up here, we can do some relative dating with these fossils and say that fossil D is older than fossil C, because we know that the oldest is always going to be at the bottom. So that is relative dating. So that is what we are going to do a lot of, and we're going to get a lot of practice with it, and I think it's pretty easy, so we should be good. Now, this is the trickiest part, so we're going to get a lot of practice with this part. You can't use every single fossil to do relative dating. Now, what do I mean by that? What am I even talking about? So there are certain fossils that might be present over many, many time periods. So you can't really use that to compare it to other fossils. So once we get into an example of this, you're going to see exactly what I mean. So we are going to use fossils that we can use for relative dating. We're going to call those index fossils that we talked about earlier. So to become an index fossil, to be a fossil that you use to date other fossils, the standard fossil, you need to have these two things be true. So first, you have to be present in a short period of time. So think of each layer as a period of time. So over here, layer 6 is going to be one period of time. We could say, just for an example, we can say that there was 10 million years ago. Layer 7 is a totally different period of time. We could say that's like 15 million years ago. Layer 8 is a different period of time. So each section is going to be a different period of time. So first, for it to be a good index fossil, it has to be in just one time period. You can't have a fossil in layer 6 and in layer 7 and in layer 8, because if you are, let's say we're trying to find the relative age of this fossil right here, if we are comparing it to a different fossil, we can't have it be compared to a fossil that is in column 6 or 7 or 8, because if you say that this fossil is younger than that fossil in column 6, but what if that fossil is also in column 8? That doesn't really give us something good to compare it to. So you want to compare the fossils to something that's in only one time period. So like in this case, you see fossil 8, we can say that the fossil in layer 7 is younger than the fossil in layer 8 because there's only one fossil in layer 8 and it's closer to the top than layer 8. So we know that this fossil is going to be younger. Okay. So, and like I said, we're going to get a lot of practice with index fossils. So if right now you're like, this lady's talking crazy, don't worry, we're going to get some practice. Also, for it to be an index fossil, it needs to be in multiple locations. Now, I know exactly what you're thinking. Miss Long, you just said it can only be in one section. What I mean by multiple locations is if you look right here, each column, like this says column Y, column Z, these are different, we'll call them outcrops. You'll see that word a lot. It's like if I took, back to the piece of cake, if I took a slice of the earth in one location, we're going to call that an outcrop. So this is one slice. This other outcrop is a totally different slice. It's in a different location. So both of these, let's say right up here above layer 1 and layer 6, that is like the surface of the earth, and we're looking down into the outcrop of that section. So these are two different locations of the earth that we are looking at. Okay? So let's say we took this column Y. This is from where we dug into right outside of the middle school in Como. We're looking into the earth right outside. We'll even say the parking lot. We dug right into the parking lot. Column Z, we went over to Sardis and did the same thing. We dug right into the parking lot of the high school. So we are looking at two different locations, okay? So you want to use, for a good index fossil, your fossil needs to be in two different locations. So if you look at this fossil right here, we have one of those in Como and we have one of those in Sardis. But it's also a good index fossil because it's not in multiple time periods. So if this fossil here was in this section and in this section and in this section, it wouldn't be a good one. So this fossil is good because it is in one time period, but it is in multiple locations. So that is your index fossil. So this last side, we're just going to do a little bit of practice with that because I know that can be kind of tricky, but once you do it yourself, you're going to say, oh, I'm straight. This is so easy. So let's look at this first example here. We've got three different outcrops or three different locations that we dug into the earth. We can say Como, Sardis, Crenshaw. Pretty easy. So the fossil in layer A is in only one time period. So here we have one section. we circled this fossil. Notice that this fossil isn't in multiple layers in the same outcrop, so you don't see this fossil in layer B or C or D or E, but it is also found in multiple areas. So we have one here in outcrop 1, we have one in Como, we have one over here in Sardis, and we have one over here in Crenshaw. So we know that that is going to be a good index fossil. Okay, so that's how we find our good index fossil. Now, what's the point of finding that? Who cares, right? So since we know that this is going to be the same age as this, which is the same age as this. So we know that this fossil here in layer A, let's say it is 10 million years old. Some scientists did some absolute dating, figured out that this fossil was around 10 million years ago. So if this one is that old, we know that this fossil, since this is an index fossil, must be the same exact age. Okay? So if this one is 10 million years old, we'll say this one is 10 million years old, which means this one is 10 million years old. Since we know that these are the same age, we can do some relative dating with the other layers. So since this one is 10 million years old, and we know the further down we go into an outcrop, the older it gets, so we know that any fossils below this is going to be older than 10 million years old. So fossil in layer C is going to be older than this fossil. And it's also going to be older than this fossil, and it's also going to be older than this fossil. So any of the fossils above that index fossil are going to be younger than 10 million years old because it's above and younger than these fossils. Okay, so we can say that rock layer A is blank to layer K. So let's see, where's layer K? Here's the fossil in layer A. There's its index fossil, so we know it's going to be the same age. Okay, now layer K is blank to layer B. Where's layer B? So here's layer B. We know the age of this one, and it is above, it's closer to the surface of the Earth than layer B, so we know that layer K, let me back up, I said that a little quickly. We know that layer A and layer K are the same age, right? We just talked about that. So whatever the age of layer K is, like we said, 10 million years old, layer A also 10 million years old. So since layer K is the same as layer A, and A is above layer B, we know that whatever layer A is, it is younger than layer B because it is above it. So since A is younger than B, we know K is also going to be younger than B because it is right above it. So let me say that again. So layer A and K are the same age. Since they are the same age and layer A is younger than layer B, we know that layer K is also younger than layer B. Okay, one more example. Let's walk this through us one more time. Here we have 4 different outcrops or 4 different sections of the Earth, and we need to figure out which one is the index fossil. So remember, it can only be present in one period of time, so in one layer of a section, and it has to be in multiple locations. So if we look at fossil, let's look at fossil B here. Fossil B is in multiple sections of one outcrop or one section of the Earth. So we know that that is going to be alive in multiple time periods. Same thing over here, it's in multiple layers. So we know that fossil B is not our index fossil. If you look at fossil C, same thing. Fossil C is in multiple time periods within one section of the Earth. So that's not going to be our good index fossil. Now fossil D is present in only one outcrop. So over here it's in only one time period, right? Because you're only seeing it in one layer of that Earth, but it's not in multiple sections. So that's not going to be our good index fossil either. Fossil A is the perfect index fossil because here it is in only one time period, but it's also present over here in only one time period. It's over here as well in one time period, and it's over here in one time period. So fossil A would be our index fossil. Now fossil B, like we said, is not going to be the index fossil because it is in too many time periods. Okay. Your brain might be spinning a little bit from all this index fossil nonsense, but once you really work it through and get some practice in, this is going to start coming easy to us. This is one of the things that we were best at last year, and last year the eighth graders didn't believe me either, I promise you. At first you're like, I'm confused, but then anytime they got it on the test, they were like, easy peasy, we got it.